Welcome to class, ladies and gentlemen. Mr. Eicher here to teach 12.2 transformations to achieve a linearity. In your class notes, we have when associations are non-linear. What two approaches can we take to model the association, and what approach will we use? Well, so there's two approaches. One approach, let's say you have some kind of scatter plot that looks like this. In this case, you can actually model it with not a linear model, but like an exponential model or a power model, some other type of function. If you go and look at your calculator, under stat calculate, we've always been using number 4, lin reg, but right below that there's quadratic regression, cubic regression, quartic regression, there's natural log regression, exponential regression, power regression, logistic. I'm just reading right down the list under stat calc. There's a bunch of different functions that we could actually use. So like in this case, we could use maybe like an exponential curve to model the data. That's one approach. That is not the approach that we use in AP Stats. What we actually do is, if we have a scatter plot that shows some kind of curved pattern, maybe like this, what we do is we re-express the data so that instead of looking curved, it will look like a straight line. So this is why this lesson is called Transformations. To achieve linearity, we're going to transform a curved pattern into a linear pattern. And if you've completed the StatCrunch assignment, the purpose of that assignment was to get you thinking in this direction. So let me just quickly go to the StatCrunch assignment. So we had child mortality under age 5 for different countries, and we had the income per person in those different countries. Some data from gapminder.com. The scatter plot itself, here's the regression output. You can see the R squared's pretty weak. You had 0.337 for R squared, correlation negative 0.58. But I want to look at the graph particularly. Notice in this graph we have this downward curve pattern in the data like that. We should not use a line to approximate this data, unless, of course, we transform the data by some kind of other function. And you can see on the residual plot, if you're able to get that to work in StatCrunch, you can see in the residual plot you have this curved pattern, which tells us that there's some more association that the linear model didn't take care of. We would like random scatter if a linear model is going to be appropriate. So what I had you do, I think we're done with that one now. What I had you do was try to transform one of the variables. Try to transform the x variable, transformation of the x to be a natural logarithm, and let's see what that actually does. You can see our R squared is higher now, 0.76, but when you consider the graph, there is this slight curve, kind of goes like, starts up here, kind of goes down here, and then it tapers off over there. Slight curve, don't know if you could observe that, but I think definitely looking at the residual plot, if you turn the page, the residual plot has a definite curve in it, which is kind of one of our no-nos with residual plots. That right there, curved pattern. We should not use a linear model. So in this case, just doing transforming one of the variables, ln of income, didn't help our cause. The last one that I had you do, notice our R squared is 0.92, correlation is negative 0.96, but you might recall just because you have a strong correlation doesn't mean that it's necessarily linear. You definitely want to look at either the residual plot to determine linearity, or you want to look at the scatter plot. So that's what we'll do. Checking out the scatter plot, that looks pretty good. Now notice this is ln under 5 mortality rate, and we had ln income. And it looks pretty straight. It looks pretty nice. It might be appropriate to use a line to model this data, or this transformed data, I should say. And then looking at the residual plot, that looks like a pretty good random scatter to me. No distinct curve pattern. So in this case, our function that we would use to model this data is a linear function. ln under 5 mortality, 11.6 minus negative 9.8 times ln income. This is the one lesson all year dealing with logarithms we'll use pretty frequently to transform data. And then once we have that transformation, we could convert it back into, like, what does the original exponential or power model look like? But for the most part, we just stick with this linear equation, y equals mx plus b, or a plus bx. So the approach that we use is transforming to achieve linearity. So what is a power model? What are some examples of power models? You've been dealing with power models for a long time. An equation like y equals, 3x squared, that is a power model. You saw that probably all the way back in Algebra 1. So anytime your variable is a base, not an exponent, it's a power model. So for instance, you could also have y equals, x to the 1/2. That power is a real number, so that is a power model. Some examples of power models. The height an object is after it's been dropped from some height is going to be affected by gravity. We'll just say some constant a, and then x squared, which is the height of an object. So we can model heights with power models. Pendulum, the time it takes a pendulum to complete one back and forth swing, called its period, is related to the length of the pendulum. So like the period of the pendulum, the back and forth swing, equals some constant a times the square root of the length of the pendulum. That's a cursive L. That would be a power model. The square root is a 1/2 exponent. Also, the intensity of a light bulb is related to the distance from the bulb. So the closer you are to the bulb, the more intense it is. The farther away, the less intense it is. So that would be like intensity of a light bulb is some constant a over the squared distance. This power model would have an exponent of, if do a little algebra here, ad to the -2. So this is also a power model. Those are just some examples of power models. Exponential models. Instead of having the x as the base and the exponent as a number, now we'll switch those. So examples of exponential models might be 3 times 2 raised to the x. It's called an exponential model because our variable is now an exponent. So an example of this might be like compound interest. Compound interest. Also, you could have a base that's less than 1. So you have 3 1/2 to the x. My beautiful handwriting here. And in science contexts, I believe in Algebra 2 you may have talked about radioactive, I didn't spell that very good, radioactive decay is an example of exponential decay. There's exponential growth, like compound interest. If you put money in the bank, you're making interest on your interest. Or radioactive decay, or half-life. So those are just some examples. So our goal in this lesson is not to model data with an actual exponential model that we have to come up with, what is the A, what is the base in our model. It's actually much easier than that in some sense, because we're going to take our data and transform it so it's just a linear model, like A plus BX, or Y equals MX plus B. So how do you linearize, how do you transform a relationship so it follows one of these models? I've included a helpful chart right below here. We have three possible models that you should be familiar with: an exponential model, a logarithmic model, and a power model. So an exponential model the first one we have here, you'll notice that your x-axis remains the same, x, but you're transforming your y-axis to be a logarithm of that y response variable. So for instance, if you had y equals a b to the x, that would be an exponential model. You're keeping x the same, but you're going to do a logarithm of y. And the equation that we would use is this equation. So let me explain a little bit where this comes from. Have to review our log properties. So let's see. Go to a whiteboard setting. Ooh, don't like to see that though. Erase that. Okay, so let's say we had, we conjecture that we have some exponential relationship like that. So it might be a y equals a b to the x. If we take a logarithm of both sides, it's just an operation we could do to both sides of the function. Log y equals log a b to the x. Now with properties of logarithms, you can take this logarithm of a product and split it up into log of a plus log of b to the x. And furthermore, if you remember properties of logarithms, that exponent right here, this exponent right there, we can bring out in front. So now we have log a plus, bring down the x times log b. Now, log a is just some value. If we knew a from the original, if we know this value of a right here, then we can just do log of that and we would get some constant. Likewise, this log b, we would just get some constant. So since it's related to a, but it's like kind of different now, I'll just call it like a prime plus x b prime. So you can see, using properties of logarithms, our linear equation we would have is log y equals some constant a plus x times some constant b. And that's basically what we have. In our notes right here. Likewise, a logarithmic model should look like this equation. So a logarithmic model, if you remember from your pre-calc or algebra days, logarithmic model might look like one like this. Something like that. That would be y equals log x plus some constant a, which basically gives us a really similar equation that we had if we do a log of our x variable, we'll get this linear idea, b times log of some number, and then a plus that. And that's kind of what we have right here in our notes. Y hat equals a plus b times x, log x. The hardest one to see is probably the power model. How in the world would you get something like this when you start with y equals ax to the b? How does this become something like that? So let's say we have y equals a b to the x. We take a logarithm of both sides, and you know what? How about we take a natural log base e of both sides. ln y equals ln a b to the x. Nothing special about why I'm choosing ln here rather than log base 10. Other than I want you to look at ln and recall that there is such a natural thing as ln, the natural log. So let's see. If we do a little simplifying like we did before, we can split up ln a plus ln b to the x. That's an L. That's an N. ln b to the x. Now you might recall, like I said before, ln a is just some constant, so we'll call that like a prime for now, just some new constant related to a, plus bring down the exponent x ln b. Likewise, we have ln b as some constant, so we have a prime plus x times b prime. My bad, I just realized I'm doing an exponential model. Notice the b there. Got to make sure you use the right function. So our power model is y equals ax to the b. Okay, so we log both sides. X raised to the b. There we go. Do some log properties next. And we get this equation is the linear model based on a power model. So anytime you see two logs, one on each side, or two natural logs, one on each side, that tells you, oh, this is a power model. Power model. So let's begin and look at what in the world do we have to be able to do with all this information on the AP exam. So let's go back to our class notes. So I'd like you to pause this video and consider the graph, consider the residual plot you're given, read the little paragraph, and read part A. And then once you're ready, you can unpause and we can work on A together. So you've read about Moore's law, about the number of transistors in a circuit chip. From what I understand, a transistor relates to the speed of computing. So you can see in 1971, 2,000 transistors, slow, compared to 2010, 2.3 billion transistors, much faster computing time. So if we'd like to model this data with a linear function, the problem is, of course, that you have this curve, very drastic curve, looks like an exponential curve in the scatter plot. Likewise, you have this curved pattern in the residual plot, meaning we tried to remove any linear association, but when we did that, the residuals still show a association between the two variables, a curved association. So our original equation was this equation. Predicted transistors equals that right there. This first question says, a natural logarithm was used on number of transistors. Very important to notice the axis here, ln transistors compared to years. And notice how nicely linear that created the data. So rather than us having to try to figure out what in the world would the equation of the exponential function be, ab to the x, we can transform this data and figure out the equation of our linear model. So the question is, explain why it would be reasonable to use an exponential model. Well, that's because we have x, we have ln y, which relates to an exponential model. Just a little algebra. If you have ln y x, then that would be the same as y equals e to the x, and that is an exponential model. So because the transformation linearized the data, as we can see in the scatter plot, it would be reasonable to use an exponential model. What is that exponential model? Well, when you turn the page, often in these you don't have to figure out the how to do the transformation. You just need to be able to read computer output, which is this first two columns. And this is for the transformed data. So it says give the equation of the least squares regression line. We would have ln y as our axis set on the scatter plot equals our constant 7.0647 plus our slope 0.36583 times our explanatory variable, which we did not transform, which is years. And then ln y, y hat, that was close. Ln y would be the same as ln transistors, predicted transistors, if I could spell transistors with a hat on it. So that would be our equation. Defining any variables I just use years and transistors in my equation. So very similar to what we've done throughout the year, writing an equation of a regression line, but now it's just ln y. Now, very importantly, you need to be able to evaluate logarithms. That's probably the main reason why Algebra 2 is a prereq for this course. We're going to use that equation, and then down here in part C, it says use your model to predict the number of transistors of an Intel computer chip in 2020. So our years was years since 1970. So 2020 would be 2020 minus 1970, which is our explanatory variable would be 2020 minus 1970. How many years since 1970? And that would be 50. So all that we have to do is plug in 50 into our transformed equation. This might get a little messy since my handwriting isn't the best. ln y hat equals 7.0647 plus 0.36583 times 50. Just plugging that in right there. Simplifying that, we get ln y hat equals, I got 25.3562. You can check my work there. And then to solve that, you have to figure out how do I isolate y hat? How do I get rid of this operation of ln? Well, the inverse operation of ln is exponentiating. So we would have y hat, our predicted number of transistors, would be e as our base, raised to the exponent of 25.3562, which equals 1.02815 times 10 to the 11th. And that's number of transistors. which, if my scientific notation's right, would be about 102.8 billion transistors. Part D says, how much does our least squares regression line of transistors on date underestimate the number of transistors compared to our transform prediction equation? Here we would simply plug in 50 into our original equation, this equation right here. Plug 50 into that, and you can kind of tell it's going to be a gross underestimate. 50 is like right here on the graph. 50 is like right about here on the graph. Maybe like right there if you continue the line. But it looks like the graph is growing, so we're going to have this severe difference if we just used our line, our least squares regression line, to make the prediction rather than our transformed least squares regression line. If you'd like to pause and see if you can calculate that difference, you can pause this video. So plugging 50 into our original y hat equation, I got 1.525 times 10 to the 9th transistors. Comparing our answer in part C, this is basically 1.5 billion versus 102 billion. That's a lot of billion off. We're off by 1.01 times 10 to the 11th transistors. So using the line gave a horrible prediction because the scatterplot showed an exponential growth model. So we were able to figure out that exponential growth model by transforming the data. The next example I'd like to look at, I would like you to answer parts A through E, I believe it is. And then I will try to quickly go through the answers. So please pause this video, maybe take 10 minutes or so, and then we'll go over the answers. So question A, describe the association between field strength and Sparrow density. This would be an example of doing DOFs. So the direction, we have a negative association. You can confirm that with your slope. Very helpful to do that, negative 8.6. So direction is negative association between field strength and Sparrow density. Make sure you include context. Outliers, there's this kind of strange point right here at, what is that, about 3.1 comma 12. So it might not be an outlier, but it's always good to note strange things. So we have a interesting observation, unusual, probably not that influential, but I'll mention that. The form is probably the most important part. Notice that we have this curve, particularly because these last two over here, kind of makes this exponential decay kind of curve. And then the strength, you could refer to r squared. It looks like a fairly decent curved pattern, but as a linear pattern it actually doesn't have that great of a strength. If we did the square root of that value to get the correlation, we would get 0.76. So that's pretty close, kind of moderate, but pretty close to a strong association. But we'd either say it's like a moderately strong linear, or we would say it looks like it might be a fairly strong curved association. But the main point in this lesson is, hey look, it's curved, what should we do? Well, you're offered, and then on part B you said, would a linear model be appropriate for this data set? We would say no for two reasons. Good response would say no for two reasons. Number one, you have that curved pattern here. Number two, it appears that our residual plot, looks like our residual plot has some kind of curved pattern in it as well. So for part B, you'd say no, a linear model is not appropriate. The residual plot shows a curved pattern, and the sparrow plot, strange. The scatter plot itself has a curved pattern. So really, at that point, nothing new in A and B that we haven't done months ago. But the only new part in today's lesson is, hey, now we're going to transform one of the variables, and you're told which one, but it's always good to note the axes labels. So we have transformed the x planetary variable, field strength, magnetic field strength, and left Sparrow density alone. So the next question says, comment on the appropriateness of this model. The residual plot is looking much nicer, and the scatter plot itself definitely shows a much more linear trend for this data. So we would say it's appropriate. The scatter plot is roughly linear, and the residual plot doesn't show that strong curve like it did originally. And then you're given computer output, which is fantastic. With the computer output, we will write an equation of the least squares regression line with the transformed data. And then also, we'll use the line to predict the Sparrow density for an electromagnetic field strength of 0.75 volts per meter. So what that would look like is this. We would have our y hat, since that wasn't transformed, y hat equals 14.801 is our y-intercept on the transformed data. That's an 801. Minus our slope, 10.548. And very importantly, since we transformed, it's not just x, but it's ln x. So we have here is our Sparrow density to define our variables. Sparrow density. And it's predicted Sparrow density. And then this right here is our field strength measured in volts per meter. So all we need to do is plug in the 0.75 into x. So notice, be very careful when evaluating that. You just, in this case, you don't have to exponentiate both sides like we did on the last problem, but you could just do ln of that value. And we get 17.835 sparrows per hectare. Should really look up what a hectare is, some kind of measurement of maybe area. Be careful if you're like me and it's interesting to compare the scatter plot. So we got an answer of 17.8 when we plugged in this 0.75. If we go back to our scatter plot, you might think, oh no, I got the wrong answer, because as you can see in the scatter plot, 0.75 is here, but we definitely didn't get 17.8, which is way up here. So you might be a little confused. But remember, this is predicting from the original scatter plot. So if we go back to the original scatter plot, we had a 0.75 volts, which was right here. And that's the value that we plugged in, and we got a prediction of about 17, somewhere in here. So that makes a lot more sense. Making sure you're using the right scatter plot to compare your answers. And lastly, interpret the value of r squared. This can be tricky because when interpreting the value of this r squared, we need to mention that we did transformed data, that we did a natural log of the field strength. So notice this r squared value of 0.7622 is related to this scatter plot. So when we interpret r squared would be 76% of the variation in Sparrow density is accounted for by the transformed least squares regression line of density on ln field strength. being very careful, it's the transformed least squares regression line that we're talking about. And notice I've mentioned it's ln field strength. If you were just to say 76% of variation in Sparrow density is accounted for by the least squares regression line, that could sound like you're referring to this original scatter plot, which didn't have 76% variation for r squared, but had 57% of the variation in Sparrow density as accounted for by the original least squares regression line. So be careful when interpreting r squared when you deal with transformations of data. I have one last example for you to answer. I will not include the answers here. You can discuss among yourselves. Letter A, and then which model, this is kind of a common question when asked about transformations on the AP exam, which model is a better model? So in answering B, make sure you identify what type of model you have, if it's exponential, logarithmic, or power, and you can use this little table for assistance, that table right there. And then choose which one, and I would base my decision both on the scatter plot and the regression output, which you think is a better model. Thus ends this video. Thank you for listening and participating along, and all hail stats.